Welcome to Spring LIB.
This is chapter 37, problem number 60. Lorentz and Einstein are playing tennis. They're 20 meters away from each other. The mass of the ball is given to us as 0.058 kilograms. And Lorentz serves the ball at 80 meters per second. And in part A, we're asked to calculate the kinetic energy of the ball if the speed of the ball is 80 meters per second. So this is a non-relativistic regime then, because we're dealing with speeds much lower than the speed of light. Then the kinetic energy is going to be 1/2 mv squared, right? And 1/2 m being the mass of the ball, 0.58 kilograms, and the speed of the ball is going to be 80 meters per second. Of course, we're going to square it. So then kinetic energy is going to be 185.6 joules. Now in part B, Einstein serves the ball back. It strikes the ball back towards Lorentz in a very much greater speed of 1.8 times 10 to the power of 8 meters per second. So now 1.8 times 10 to the power of 8 meters per second. Now we're in the relativistic regime, and we're asked to calculate the kinetic energy in this case. In this case, we can't use 1/2 mv squared anymore because the speed is in the order of the speed of light. We are going to have to remember the relativistic kinetic energy equation, gamma factor -1, rest mass times c squared. Now let's calculate what gamma is here. In this case, gamma general formula for it is 1 minus v squared over c squared. In our case, 1 over square root of 1 minus 1.8 times 10 to the power of 8 meters per second squared divided by square of the speed of light. So if we do the algebra, what we have here is then 1.25 for our gamma factor. Now, putting this back in the formula here, the kinetic energy formula here, 1.25 minus 1 times the rest mass of the ball is 0.058 kilograms. C squared will be 3 times 10 to the power of 8 meters per second squared. Then kinetic energy is going to be 1.305 times 10 to the power of 7 joules. Now, let's start part C on a separate page. In part C, we're given now we have a rabbit that is running from Einstein towards Lorentz as they're playing tennis. So rabbit's speed relative to those men is, I'm going to call it v prime, is 2.2 times 10 to the power of 8 meters per second. That's a quite fast rabbit. Now, the ball's speed was 1.8 times 10 to the power of 8 meters per second. We are asked to calculate the speed of the rabbit. So what is the speed of the rabbit relative to the ball, right? So, well, if we're looking for the speed of the rabbit relative to the ball, we're looking for v, which is v prime minus u over 1 minus u v prime over c squared, like relativistic speed addition. So when we plug in the values, 2.2 times 10 to the power of 8 minus 1.8 times 10 to the power of 8 meters per second, of course, let me put it here, divided by 1 minus 2.2 times 10 to the power of 8 meters per second times 1.8 times 10 to the power of 8 meters per second over 3 times 10 to the power of 8 squared. That's right. Now from here, the speed would be equal to 7.14 times 10 to the power of 7 meters per second. That would be the speed of the rabbit relative to the ball. Now in part D, we are asked to calculate the distance from Einstein to Lorentz according to rabbit. So the distance, let's call it an L, right? Distance from Einstein to Lorentz in the frame of the rabbits. So this can be given as in terms of the proper length, which is the length that is measured by Einstein and Lorentz divided by the gamma factor. Again, L naught was given to us as 20 meters in the beginning of the problem. All we need to do is to, rewrite what gamma factor was, as you can remember from part B. So L naught, 1 over gamma factor is going to be 1 b squared over c squared. This is all for the rabbit, right? So 20 meters times square root of 1 minus v is going to be the speed of the rabbit, 2.2 times 10 to the power 8 meters per second squared, 3 times 10 to the power 8 meters per second squared. Then we find, according to the rabbit, the distance from Einstein to Lorentz is 13.6 meters. Now, in part E, we are asked how much time does it take for the rabbit to run 20 minutes according to the players. So now we're back in Einstein and Lorentz's frame. So the time that it takes obviously is going to be the distance according to Einstein and Lorentz, which was L naught, which is 20 meters, divided by the speed of the rabbit, right? This is straightforward. 20 meters divided by 2.2 times 10 to the power 8 meters per second. So the time that it takes for the rabbit to travel across the from Lorentz to Einstein, from Einstein to Lorentz is going to take 9.09 times 10 to the power of negative 8 seconds. Now in part F, we're asked what time does the rabbit measure this interval, because according to the rabbit didn't travel 20 meters, right? If you remember from part D, we had found the distance the rabbit traveled to be 13.6 meters. All we need to do now is, if we're going to calculate the time that the rabbit is actually keeping track of, then it's going to be the distance according to the rabbit divided by the speed of the rabbit. So it's going to be 13.6 meters divided by 2.2 times 10 to the power 8 meters per second, which is a little over 6 seconds. Oh, wow. And there's a 10 to the power of negative 8, of course. So it's much smaller than 6 seconds. My apologies. So it's going to be 6.18 times 10 to the power of negative 8 seconds.